Hi guys, welcome back to In Case of Econ Struggles. Approximately a year ago, I did my first video on utility maximization problem. It was a 43-minute monster, so we're going to redo that in a way that's more helpful and more concise. And as usual, timestamps are below if you would like to jump around. Here is the motivating example for the utility maximization problem. Here's Bill. Bill's got $10 in his pocket, and Bill's about to walk into this store called Food R Us. And Food R Us serves exactly two things: ice cream for $2 and eggs for $4. And Bill walks into the store. He likes both ice cream and eggs. He would really like to buy the whole store. He would like to walk out with as many eggs as he could carry and as many ice creams as he could carry. But Bill cannot walk out with as many ice creams and as many eggs as Bill can carry because Bill only has $10. So Bill has to make a choice about what sort of things to put in his cart, given that he only has $10. And anytime we're thinking about the choice that Bill is making, we want to think about what Bill's best choice could be. And so the utility maximization problem is trying to answer, given that Bill has $10, given that ice cream costs $2 and eggs cost $4, what is the cart that Bill can walk out with that'll make him the happiest? So utility maximization problem, we're trying to find the optimal bundle, the optimal shopping cart, given Bill's constraint. Now let's think about this problem graphically, and let's say that we've got an indifference curve, which is just Bill's utility function at a certain level of utility. And he's got a budget constraint. This budget constraint is downward sloping with a slope of negative P of ice cream over P of eggs, just because that I've put ice cream on the y-axis and eggs on the x-axis. Another way you can think about it is if Bill spent all $10 on ice cream and ice cream is $2, he could buy 5. And since eggs are $4, if he wanted to buy only eggs, he could buy 2.5 cartons of eggs. And then you connect the dots with a straight line. And so what we're going to do is, the way we're going to solve this utility maximization problem is we're just going to set the slope of the budget constraint equal to the slope of the indifference curve, which is minus pi over pe. That's going to be equal to the marginal utility of ice cream over the marginal utility of eggs, which is also called the marginal rate of substitution between ice cream and eggs. Now let's talk about this a little more intuitively as to why this is the slope of each. Hopefully it makes sense that the slope of the budget constraint is the price of the thing on the y-axis over the price of the thing on the x-axis. Why does that make sense? If I put a pint of ice cream back, I'm going to get $2, so I can buy some more eggs. How many eggs can I buy? Well, that $2 divided by the 4 in the price of eggs, so that's going to give me a slope of minus 2. The marginal utility of ice cream. If I give up an ice cream, I'm going to lose some utility, so maybe like this. All right, well, I need to stay on the same indifference curve, and indifference curve means that I have the same value of utility. So how do I get back on the indifference curve? Well, I take the utility that I just lost. I divide it by how much utility I get for each egg or each carton of eggs that I buy. And I buy that many cartons of eggs so that I get back onto the indifference curve. If that's still a little unclear, comment below, but let's go on and talk about how to solve this thing analytically. So here's a numerical example. We're going to do a different sort of example. Here's Deb. Deb eats two things. She goes to Chipotle and she also likes to eat veggies. So her utility function, this is called a Cobb-Douglas utility function. We're going to have Chipotle to the 1/2 times veggies to the 1/2. We're going to say that the price of a Chipotle bowl is $10. The price of veggies is $5, and she's got $40 in her pocket. We can use that to determine the budget constraint, which just says that she's got $40, and that's going to be $10 for every Chipotle bowl that she buys, and $5 for every thing of veggies that she buys. And we're going to spend all $40 because Deb likes more Chipotle and more veggies always, so it's always going to be the case that she spends all her money. Again, we're doing a utility maximization problem, so we're trying to find Deb's optimal bundle. So what is the solution to Deb's utility maximization problem? Well, we just said that we're going to set the ratio of prices equal to the ratio of the marginal utilities, the marginal rate of substitution between Chipotle and veggies. There are technically minus signs here, but there are minus signs on both sides, so I just make them a plus to make my life a little easier. I'm going to take the derivative of this utility function with respect to Chipotle. I'm going to use partial differentiation, and that's going to give me this right here. If that's a little unclear, make sure to check up on your partial differentiation rules, and if it would be helpful, comment below and I can do a separate video where I talk about that. The price of Chipotle over the price of veggies is 10 over 5, which is 2. So 2 equals V over C, so V equals 2C, which means that however much Chipotle I buy, I double it, and that tells me how many veggies I buy. And that's useful because I've got a budget constraint with two variables in it. I've got 40 as 10C plus 5V, which means that I can substitute 2C in for V, which means that 40 is 10C plus 10C, which is 20C, which tells me that C star is 2. And if C star is 2, then 2 times 2 is 4, so my V star is 4. and that is the solution to Deb's utility maximization problem. So hopefully this gives you a couple ways to think about the utility maximization problem, and it's easier to watch than a 43-minute video. If this was helpful, make sure to like and subscribe, and we'll see you next time for another case of econ struggles.